Very good morning to you all my dear students. So today class we are going to discuss about the new chapter called moving charges and magnetism. So till now from first if you come that while in the first chapter electric charges and fields we feel that what is charge? What is charge? We come to know that it is a physical entity which experiences and produces electric and magnetic fields. So if a charge is at rest, what happens? We come to know that it is going to produce electric field. If you want to bring that charge from somewhere to a point, we have to do work done. That is called what? Potential. And now if the charge starts to move, we come to know that it is going to produce electric current. So up to 1820, what happens? Everyone thought that the electric field and magnetic field are completely different phenomena, means electricity and magnetism are not relatable, means there is no relation between electric field and magnetic field. So both are different phenomena arises due to their individual properties. But in 1820, Christian Orsted is performing one experiment. So he is performing one experiment. At that time he observed one experimental phenomena that he has not ever observed previously. That is, so he is doing work on circuits. So let us take a circuit. In this circuit the current is flowing from A to B. Okay. Now there is a magnetic needle. You know magnetic needle, right? North and south. It has two poles, north pole and south pole. So he is doing some experiment. He placed a magnetic needle here. So when you switch on the circuit, the current starts to flow from A to B. When the current starts to flow from A to B, he observed a fact that magnetic pole deflected towards west, means the magnetic north pole deflected towards which direction? West direction. So if you take that, the directions, this is, assume that north, south, this is east and this is west. So it is deflected towards which direction? West direction. Means when a magnetic needle will deflects, when there is magnetic field only it will deflects, right? Okay, let us some magnetic field will be there, that's why it has been deflected. He assumed that. What he has done, because he is scientist he is very interested to observe the phenomena. Now he changed the direction of current from B to A. Then what he observed, and placing the same magnetic needle near the current carrying wire. So this is what? This is a current carrying wire. So what observe he is, when he reverses the direction, initially the current is flowing from A to B, the dipole deflected towards west. When the direction of current has been changed from B to A, he observed that the north pole deflected towards east. The north pole deflected towards east. So and again he has not satisfied, keep on doing. So he has taken a current carrying wire. He sprinkled some iron fillings, means some small iron nails around all directions. So you know the iron nails why he has sprinkled here? Because if there is existence of magnetic field, these iron nails will get attracted towards the current, right? So what he observed after doing this one is, the iron nails are observed in a pattern that they are moving in concentric circles. Like if you take that any pen, around that place a bangle. So this is a current carrying wire. Assume that this pen is a current carrying conductor. Then the magnetic field will be in the form of concentric circles. So like bangles. See, when pen is placed like this here, Around this pen, if you place a bangle, what happens? That will be in the form of magnetic field, means a current carrying conductor wire carries current. So, the magnetic field will be in the form of what? Concentric circles around the current carrying wire. So, what he observed and we observed here, a current carrying conductor. If you switch off the current wire, no deflection, because if you switch on a current carrying wire, you are observing some magnetic field. So, this clearly explains that a current carrying conductor is going to produce magnetic field and its direction is always perpendicular direction of current carrying conductor. So, what observed he? Orsted observations found that a current carrying conductor produces magnetic field. See, from this we conclude that a current carrying conductor is going to produce magnetic field. Its direction is directly perpendicular to the direction of its motion. So, from this what we can say that what is a magnetic field? So, what is magnetic field? It is represented by letter capital B. So, B represents magnetic field whereas E represents electric field. So, how to define the magnetic field? The space around a magnet or a current carrying conductor in which its magnetic force has to be experienced, right? Its magnetic influence can be experienced. So, the space around a magnet or current carrying conductor around which its magnetic influence can be experienced. Okay, the space around a magnet or current carrying conductor around which its magnetic influence can be experienced. Now, what are the sources of magnetic field? What is the source to produce magnetic field there, right? A current carrying conductor, right? So, a current carrying conductor produces magnetic field. So, how the current will flows through a conductor? When the charge starts moving. So, we can say that a moving charge or a current carrying conductor. So, a moving charge or a current carrying conductor produces magnetic field, or these are the sources of magnetic field. Is it right? So, that is why our chapter name called as moving charges and magnetism. Okay sir, you said that a current carrying conductor produces magnetic field. How to find the direction? How to find its direction? We have different rules are there. Let us say first rule. To find the direction of magnetic field, what is the first rule here? Ampere's swimming rule. See, Ampere's swimming rule, assume that this is completely a current carrying conductor, means this is a current carrying conductor, in that you are swimming, from one end to another end. So, imagine a person swimming in a current carrying conductor. If this is head, if his head represents the direction of flow of current, then his left hand gives direction of magnetic field. So for example, I am swimming in a current carrying conductor from south to north. So the current is moving like this. Then my left hand showing which direction? West direction. For example, if I reverse my direction, so I am coming from north to south, then my left hand is towards east direction. So this is the way to calculate find the direction of magnetic field. What is that? Ampere swimming rule explain that. Imagine a person swimming in a current carrying conductor, if his head points direction of flow of current, then his left hand gives direction of magnetic field. Okay. So if a person is swimming in a current carrying conductor, if his head gives direction of current, then what? His left hand gives direction of magnetic field. For example, there is one more Fleming's or Maxwell corkscrew rule. This is simple. Maxwell corkscrew rule. Here, have you seen the screw? Yes. So this is a screw. If the pinpoint gives flow of current, so if you take a screw, if its pinpoint gives flow of current, then the rotations of the screw head, these are what? Rotations of screw head gives what? Direction of magnetic field. So if you take a screw, if you take the screw, what happens if it is showing north direction? If it is showing north direction, then the rotations of the screw head will be in which direction? Anti-clockwise direction. So the magnetic field around that one is what? In the form of circular rings, it will be in anti-clockwise current. So same way, there is one more rule is there, that is called Fleming's right hand rule. What is Fleming's right hand rule? Simple ma. Take your right hand and hold like this. Means like thumbs up. Okay. So like this. Sorry. So this is, you hold the right hand like this. Okay. Now hold the pen. The thumb points. If the thumb points, so you are holding the current carrying conductor. If the thumb points the direction of current, then you are holding this pen, right? So this rotations of the screw head gives direction of magnetic field. So if you hold a current carrying conductor, if your thumb points the direction of current, then the rotations of the curl of fingers, this curl of fingers gives direction of magnetic field. See, for example, it is moving north direction, south to north. My fingers are rolled down in which direction? Anti-clockwise. For example, if I hold the current carrying conductor in this down direction, what happens? Now the current will be in clockwise direction. So if a current is flowing in a conductor. So this is the thumb points, the current carrying conductor. Then the rotations of our curl of our fingers will be in anti-clockwise current. So this is the direction of current and this is direction of magnetic field. So here we can apply. If the current is moving in, we can take a circular coil, the current is moving anti-clockwise current, then the magnetic field will be outwards. If the current is same concept can written as clockwise current, then the magnetic field will be inwards. So if the current is flowing in the conductor, we can say that the direction of current by using Fleming's right hand thumb rule. Okay, so here the representation of magnetic field will be of two ways. If in any concept they represent a dot like this, okay, so then we can say that magnetic field is, so here the current is inwards. So we have representation of two magnetic fields. So here we can represent the magnetic field in two ways. If in any problem or derivation, if represent like this, this is what you have to note this point very for sure. This is called outward magnetic field. If it is represented by the cross, if it is represented by dot, it is called outward magnetic field. If it is cross, the magnetic field is moving into the plane. So this is the magnetic field is moving out of the plane, means this is pinpoint. If you take that, this is out of the plane and this is out of the plane and this is into the plane. So cross marks represent that what into the plane. So the magnetic field is moving into the plane. So from all these observations, what we concluded that is a current carrying conductor or moving charge produces magnetic field and its direction is perpendicular to the flow of charges or current carrying conductor. So that was what we learned, right? See, if it is moving towards north, then left hand is what? West direction. So this is perpendicular, not perpendicular and opposite direction. So electric field and magnetic field are perpendicular and opposite in direction. Electric field and magnetic field are perpendicular and opposite in direction. Clear? Yes. Now, as usual, if you place a charge in the presence of electric field, it experiences force. That is the basic definition, right? Charge is what? It is a physical entity which experiences both electric and magnetic fields. So if you place in electric field, as we know, it experiences the charge, that is Q into E, where Q is charge and E is electric field. Similarly, if you place a charge in magnetic field, it experiences force. That force is called what? Magnetic force. So we can simply say that what is magnetic force is the force experienced by a moving charge or current carrying conductor. In where? Where it has to experience a force? In magnetic field. So the force experienced by a moving charge or current carrying conductor in magnetic field is called magnetic force, that they given as F is equals to Q into V bar cross B bar. Because velocity should be considered. Why? If this doesn't move, there is no magnetic field, there is no force. So that can be written as we know that A bar cross B bar is equals to AB sin theta. So F is equals to QVB sin theta. F is equals to what? QVB sin theta, where Q is the charge, on which charge it is going to exert the force, that is which force? As we said that is called magnetic force. V is velocity of charged particle, B is what? Magnetic field, and theta is the angle made by the magnetic field with respect to the velocity of charged particle. Okay. So now here we can define from that, if theta is equals to 90, assume that theta is equals to 90, F is equals to what? QVB. From this, B is equals to what, ma? F by QV. F is Newton by Coulomb meter per second, or this is represented as Tesla. This is represented what, ma? Tesla. So this is called, that is important definition here, magnetic field induction. This is a vector quantity. So what is the definition of magnetic field induction? So when Q is equals to 1 and V is equals to 1, then B is equals to F or not? So the same thing we are going to do. It is defined as the force. It is defined as the force experienced by unit positive charge moving with how much velocity? Unit velocity at moving with unit velocity perpendicular to magnetic field or perpendicular to direction of magnetic field. So to define B, we consider what are the conditions: theta is equals to 90, Q is equals to 1 and V is equals to 1. That only we defined here. It is defined as the force experienced by a unit positive charge moving with unit velocity perpendicular direction of magnetic field. That is called what? Magnetic field induction. That is represented by B. Now, what is the SI unit here? So similar, the magnetic field is measured in Tesla T. What about CGS unit? CGS unit is what? Gauss. It is represented by letter capital G. So the relation is 1 Gauss is equals to 10 raised to minus 4 Tesla. What about the dimension formula? Dimension formula we will write. What the formula here? Newton Coulomb meter per second. Newton M L T power minus 2, Coulomb A T L second, if it comes here T. So that is equals to what? M L minus 2 plus 1, or you can cancel these two. Yes, mlt power minus 2, sorry, ll also cancel. So we get right mt power minus 2 a power minus 1. So m t power minus 2 a power minus 1 is the dimension formula for magnetic field. So finally we have to define Tesla. How to define Tesla? B is equals to F by QV sin theta. So F should be 1, Q should be 1 coulomb, velocity should be 1 meter per second, and theta should be 90. So we can define the definition of Tesla as sorry, the magnetic field strength is said to be 1 Tesla if 1 coulomb of charge moving with velocity of 1 meter per second perpendicular to magnetic field, he experiences a force of 1 Newton. So it is defined as 1 Tesla when if 1 coulomb of charge moving with unit velocity or with velocity 1 meter per second perpendicular to the magnetic field experiences a force of 1 Newton. Very important definition, 1 mark game. So here I am going to define the definition of Tesla. Sorry. Magnetic field induction is said to be 1 Tesla when 1 coulomb of charge moving with 1 meter per second velocity perpendicular to magnetic field experiences a force of 1 Newton. So this about magnetic field. So today class we come to know that electric field and magnetic field are related. How they are related? A moving charge not only produces electric current, it also produces magnetic field that has been observed by Christian Orsted. How it will be? Electric field and magnetic field are perpendicular to each other. We have different rules such as Ampere's swimming rule, Fleming's right hand rule, Maxwell corkscrew rule. All these rules are help us to find the direction of magnetic field if current flowing in a conductor, it is straight conductor or a circular loop. Now, if you place a charge in the presence of magnetic field, it experiences the force. That force is represented by F is equals to QVB sin theta, that is called magnetic force. From that we define the basic definition of magnetic field induction, and we come to know that what is magnetic field induction and how we can measure that. Okay, so please go to the class. These basics are very important to understand and move on to the next classes, because the first class will be always the basics of the chapter. Thank you, students.